Hi and welcome to another MoTeC webinar. My name's Pete Swinney and today's subject is all the stuff you do prior to tuning in your M130 GP Lite ECU. So that's the setup of the tables, ignition, some general starting points for you to be guided by, and we're going to talk about some basic terms like how ignition timing affects the engine, as well as some stuff about volumetric efficiency. So let's get started. Alright, so the heart of the fuel model on an M1 is decided by the engine's ability to breathe air, so the volumetric efficiency. So if you're not familiar with that term, loosely it basically means how much air is going through the engine compared to the amount of its capacity, I suppose you could say. So if we have an engine that's 4.8 litres in size across 6 cylinders, that means each cylinder is 800 cc's. So that's actually measured, if you want to think about it, if we put the piston to the bottom of the bore over here and we had the cylinder head off, and if we poured water into the engine, then that particular engine would have 800 cc's of water inside by the time it got to the top of the block. So if the cylinder filling was 100% efficient, that would mean that there would be 800 cc's of airflow, if we put it simply, per cycle per cylinder. So that's called 100% volumetric efficient. So the volumetric efficiency of the engine refers to the engine's ability to fill that cylinder with air. Now in some cases, because the air is going very quickly at high speeds, and you can have tuned exhaust lengths to help extract the air or the exhaust gas afterwards, after it's burned, we can get a situation where the cylinder can actually overfill by more than its capacity. So that's termed as being greater than 100% efficient. So by tuning the engine's this efficiency by telling the ECU how much air is going through the cylinder, then the ECU can deliver the correct amount of fuel if you tell it how rich or lean you want it to be. So if you tell it you want to be Lambda 0.9, and the ECU knows the size of the engine and the amount that the engine's bores are being filled by as a percentage. So if it's a 4.8 litre engine and the ECU sees that it's 100% efficient in the efficiency map, and it sees that you want Lambda 1, then it knows how much fuel needs to be delivered to give the end result of Lambda 1. Now it uses the injector linearization and injector details part of the M1 to determine exactly how long to open the injector for, the pulse width. But the whole process really starts from you entering the correct efficiency number in that efficiency map, which is simply put the fuel map. If you make numbers bigger here, the engine gets richer. If you make numbers smaller here, the engine gets leaner. So you can see it's a key part of tuning. Most reflashes, OE ECUs use a volumetric efficiency model to determine their fueling. Okay, now let's talk about ignition timing side. Alright, first I want to talk about combustion. So what that word refers to is the burning of the air and the fuel inside the cylinder. So some people think that when the spark goes off that there's an explosion, like it all explodes all at the same time, but in fact it doesn't. It actually propagates, the flame front propagates away from the spark plug here in the middle of my diagram, and it just burns from one, say, molecule to the other, and burns out in an orderly fashion until all of the air and the fuel is consumed inside. So there's a steady pressure rise as the flame front goes across the top of the piston. Okay, so it's a little bit like if you had a pond and you threw a stone into the middle of the pond, then you see those rings, the little wave rings, going out to the edge of the pond. Alright, and so that's what kind of happens on top of the piston. So the time at which we light this air and fuel is quite important, because the pressure rise isn't necessarily consistent and doesn't happen instantly. So we need to light the ignition or ignite that air and fuel at the right time in order to get our peak cylinder pressure at the right location to give us maximum leverage on the piston and maximum leverage on the crankshaft, which gives us maximum torque, and that's what we're after. So to help explain what's happening inside that cylinder, we've got a cylinder pressure diagram across on the right hand side here. So this is from a sensor that's placed into the combustion chamber, and where someone has done some testing with different ignition points. So I'll just show you that we've got 4 curves to look at here. So the grey curve that you can see here is the cylinder pressure rise where there has been no ignition. So the keys say not turned on, but the engine's been wound over, and so that's your compression pressure from simply cranking the engine over. And then we've got 3 different ignition points here where we've got cylinder pressure rises different depending on when we light when we actually put the spark into the engine. So the straight vertical line here is top dead center, and if we look at the blue trace to start with, we can see we've got quite a late ignition point, and our pressure rise, because there's a small delay while the flame starts to propagate inside the cylinder, and then we have a pressure rise up here, but because it's well after top dead center, the pressure doesn't rise that high and it's very late, so we get it's effectively retarded timing. There's a lot of the combustion happening while the piston's going down. This kind of thing is good for making boost, because the flame is still burning when all the pressure it's going more so into the turbocharger than helping to push the piston down. Now if you're on a dyno at this point, you might look at the torque and it might be something like 600 Newton meters, pick a number, and then most of you will know if we add timing that we should make more power. So if we've got retarded timing, or timing that's causing a late pressure trace, then if we do add timing like we have here for the black trace, then we have more cylinder pressure because it's starting to rise against the piston coming up. We've got more compression pressure, the combustion's better, and we get more leverage on our piston because it's at a better location. What we're actually trying to achieve here is a peak cylinder pressure to occur at a particular location in the cycle. Generally that number is something like 17 degrees after top dead center. That's our ideal location. So if we keep advancing the ignition timing until we get peak cylinder pressure at 17 degrees after top dead center, then that ends up being our peak or our maximum torque point. Okay, so if we light it earlier, you see for the red trace here, we've fired the spark earlier, we have cylinder pressure rising much quicker, and our peak cylinder pressure point happens earlier in the cycle, just after top dead center, which is where we want it. So if this number here was 17 degrees after top dead center, then this would actually end up being our maximum torque point. I know you can't see that for normal tuning. Universities, OEMs have equipment like this, but for most of us, we're either doing it on the road or with a dyno at least. The dyno is really the time you need the ignition tuning is the time you need the dyno. You can do a lot of general fuel tuning and other tuning without a dyno, but when it comes to ignition timing, you really need to be able to measure the small gains that are gained or are achieved as you advance or retard the ignition timing. So the key thing here is if we go too far you can see if I keep lighting the fuel earlier, the cylinder pressure will rise earlier, and we'll get to a situation where the pressure is building up against the piston, still rising in the bore. So that gives us a negative effect and we start to lose power. So the general statement that we add timing and get more power is actually incorrect, because if we were at this point here and I added 5 degrees of timing to this engine, then it definitely would put the peak cylinder pressure on the other side of top dead center. We could easily do some damage, blow head gasket. Potentially, if it's a performance engine, we could damage a piston, bend a rod, all sorts of things. So too much timing is not a good thing. Even if detonation isn't occurring, if you have a very good quality fuel, just adding ignition timing randomly is not the way to go. So sure, if you have very retarded timing, very late ignition timing, then yes, generally adding timing is going to give you more power. So there really are two things that stop you, or two points at which you don't want to add any more ignition timing. One of them is you've already reached peak torque, and adding more timing won't give you any more power, so you always want to go back to your peak torque point. Or the other thing that can occur, of course, is detonation, which is what we call knock in the industry. So if the engine starts to knock, then you can't add more timing past that point. Sometimes you can add some fuel to stop the knock, but generally that is the maximum amount of time you can add in the engine at that particular engine speed and pressure or boost or load point. Alright, so that's a basic explanation of timing and what we're trying to achieve and what's kind of going on inside the cylinder. Alright, so now some of the effects of running more and less fuel and what that does for the engine. So if we are richer than normal, and I understand that you don't probably know what normal is necessarily, but if we're running a very, very rich air-fuel ratio or rich Lambda, then we can expect our engine temperature, air temperatures or exhaust temperatures to go down. If we're on petrol, we can expect black smoke, and we can expect that the richer you go away from the ideal, the less power that you're going to get. A lot of people tune to a richer mixture to start with when they're starting to learn about tuning, because other than excessive black smoke or in extreme cases bore washing, things like that, then you're unlikely to damage the engine. So tuning on the rich side is definitely a safer way of doing it, even though you end up with a little less power than what might be optimal. Alright, too lean. So what that means is leaner than what would be the ideal air-fuel ratio. So in general, if we're just talking about petrol, the perfect power or maximum power air-fuel ratio on a naturally aspirated engine, or any engine for that matter, is somewhere around 0.9 lambda. Right? There are lots of things that move that around a little bit. The effectiveness of the injector spray, the shape of the combustion chamber. Lots of, some engines will have maximum power about 0.93, others will need to be as rich as 0.86. But generally 0.9 is the accepted lambda reading for maximum power. As you go leaner than that, the combustion temperatures and exhaust temperatures go up. If you go very, very lean, then you end up where that propagation, that flame propagation becomes slow and it becomes bad, uneven, and so you end up with potentially a misfire and certainly an engine that's not running well when you run too lean. And if you go really, really lean, you can have the burn so slow that it's still propagating across the piston, or when the piston is at bottom dead center and round on its way up again, and to the point where the inlet valve is opening on that next cycle, and sometimes you can pop the intake fuel off and you can get a backfire in the intake manifold. So that's generally from retarded timing and lean mixtures, but it can certainly occur. So the leaner the mixture, the slower the burn. The richer the mixture, the faster the burn. Again, just generally. Alright, so if we're just tuning for safety, we definitely want to be on the safer side, and as much as 0.9 lambda might be perfect power on a turbocharged engine, you often need to run richer than that, and to maintain enough cooling on the piston and to prevent detonation. Alright, so now we're just going to go through the M1 fuel model. This is going to perhaps hurt the brain a little, but just want to show you how that works to get so you can get an understanding of the process the ECU goes through. So this is in the help in the M1, but also nice to be able to refer to it here if you want to kind of understand how the ECU is working. So it all starts on the fuel side with the efficiency table, which has all the green parameters here are, well, not parameters, all the green names here are axes on the tables. These are tables here, and on the right hand side these are parameters. All right, parameters or numbers that you, or settings that you put in as a tuner, and as a tuner you fill out the blue tables. All right, so our engine efficiency table, if we keep it simple, has just got engine speed and manifold pressure, and we know that for any given pressure in the inlet manifold, if we increase that pressure, we increase the flow into the engine or through the port, past the valve and into the engine. So higher manifold pressure normally means more flow, and so this is how we usually decide our fueling. Then after we have an engine efficiency number, and we'll just go with nice and simple 100% here, then the ECU then calculates engine load. Now this red box means it's a calculation. So in order to determine engine load, it looks at manifold pressure and manifold temperature or air temperature, and it comes up with a weight, so that's milligrams, an official weight of the air as a mass. All right, and to determine the total mass, it needs to know the size of the engine and the number of cylinders. So if this engine is 100% efficient and it has 800cc cylinders and there's 6 of them, it can at any time determine what the weight or the mass of that air is going through the engine. Right, so it comes up with that mass flow, and it then looks at your fuel mixture aim table. So you as the tuner get to decide how rich or lean you want to do that. Now we will keep it simple and just leave it in Lambda for now. So for example, if you have Lambda 1 as your request, so this is just for a nice idle, so we have a Lambda 1 request. The engine, if the ECU knows it's got, for example, 14 pounds of air going, 14.7 pounds of air going through the engine, it looks at your Lambda aim table, which has manifold pressure and engine speed on it. It then can calculate that for any given air that's being calculated as going through the engine, looks at your aim. It can then work out, so if it's 14.7 pounds of air, then 1 pound of fuel, if we want to put it like that. Now for it to know exactly how much fuel, obviously it needs to know what the stoichiometric ratio of the fuel is. So I said 14.7, and of course I am referring to the fact that we're running gasoline or petrol in this particular engine. So if it was methanol, then it would calculate significantly more volume, because the stoich for methanol is something like 6.5 or 6.6, I think, from memory. Alright, so it wants to know the fuel density, the stoichiometric ratio of that fuel, and from that it can calculate the volume. So it looks at the efficiency table, how efficient is this engine, looks at the size of the engine. From that it can calculate the amount of air that's there, and if it knows the temperature, it knows how much that air weighs. Looks at your fuel mixture aim, and if you want to run Lambda 1, it then looks at the type of fuel that's there, and it comes up with a volume of fuel to be delivered. Alright, so in order to know exactly how much or how long to open the injectors for, it goes into the injector linearization table, and in that table there we have differential fuel pressure and battery voltage, because as you know, if the battery voltage goes down, the injector is slower therefore it needs to open the injector for longer to get the same amount of fuel. Same applies for fuel pressure. If there's more fuel pressure at that particular moment, then the ECU adjusts the pulse width for a larger fuel pressure. And of course this is differential fuel pressure, so what that means is it's the fuel pressure across the injector itself. So that's pressure in the fuel rail versus pressure in the inlet manifold. So that's the pressure on both sides of the injector. So it uses those measurements onto this injector linearization table and calculates a pulse width. Alright, so if this number in here is accurate, what that means is that the ECU will actually be very, very able to deliver the exact lambda you want without you having to turn on closed loop, for example, or anything like that. So if it goes through the calculation, delivers the pulse it thinks is correct, and then if the lambda is richer or leaner than the lambda aim, there's only one calculation that can be wrong here, and that's the efficiency table. So if it was richer, that must mean that the efficiency table was number in the efficiency table was too high. So if we had 100 in the efficiency table, it went through the calculation, delivered what it thought was the correct amount of fuel, and we were at lambda 0.9, which is about 10% too rich, then we would push Q in our tuning table, or we would change our efficiency number of 100 down to 90. This would then make the lambda read correctly, and what that then means is the whole calculation balances, and that next time if we want to run a different type of fuel, or we want to run a different type of aim at that same location, we can simply type a new aim into the lambda table and the injector pulse width will automatically be correct. Alright, so I know that's probably too quick and a little complex if you haven't studied this before, but that's basically the process of calculating what the pulse width needs to be for any given manifold pressure and engine speed. Okay. Alright, so basically this is just words going over what I've spoken about. You tune the efficiency table, you enter a fuel mixture aim, you enter the engine capacity, you tell us, is it methanol, is it E85, is it petrol, the inlet air temperature is measured, the fuel pressure is measured, or you put an accurate default for the fuel pressure, the manifold pressure of course is measured, and the injector calibrations, which are important if you want that all to work really well. Okay, you don't have to. If you put incorrect injector calibrations in there, there's no drama, except that the volumetric efficiency table numbers that you'll end up tuning won't be right. They will just end up at random numbers that don't really mean anything. It means lots of things further down the track won't work as well as they should. It won't necessarily follow the aim lambda without closed loop, but it'll still be the worst it can be is as bad as what our gold box is today. Alright, so more numbers, bigger numbers in the efficiency table means more fuel, smaller numbers in the efficiency table means less fuel. If you get all of this right, then if you change injectors, you just enter new injector cals, the tune stays the same. If you change fuel types, go from petrol to E85, you just change the characteristics in the setup here, you don't need to retune. So it's really nice if you get all of this set up correct at the beginning, then your efficiency maps will look very similar from one engine to the next. There's a lot less work in actually tuning the fuel side. It's much faster. The lambda follows the aim better. The whole engine just becomes much easier to tune and runs much better overall. Okay, so before we start tuning the engine, so we've been working through our setup. We really, this really just covers what we've spoken about. If we get all our setup correct, you'll turn the key and the engine will just run. So the more time you get this setup more time you spend getting the setup right, the less time you'll spend tuning. So time on dynos, time straining a race engine, all of that is minimized if you just enter all of those, or that brief amount of information into the setup, and then life is so much better. Alright, so before we do start tuning, there's some quite useful tools to help you navigate and to do this quickly. We'll start with F1, which on every webinar I've ever done and training I've ever done, we've always harp on about the usefulness of F1. So F1, of course, is help, and in the M1 there's extensive help just about everywhere you go. So sometimes it's not exactly where you might expect it to be. I'm just going to flip to the live view to show you if you're really struggling to find help for an item, just so you can understand where it resides normally. We go to all calibrate, and at the root or at the beginning of any tree, we have a tree of parameters and channels and tables. So at the beginning of that tree is the help for the main item. So for example here, the mixture aim, here's the help that covers the fuel mixture aim. Where's another good example? Nitrous. Alright, so here's the help for the nitrous. So it's at most of the time it's where you want it, but sometimes you've got to go back up to the beginning of the tree, the root of the object that you're looking, or the feature. Okay. Alright, F6 for full screen. Again, I'll just show you that live. Sometimes there's lots of parameters and channels and tables and things on your screen, and this is can be particularly troublesome if you've got a laptop with a very poor resolution. So we've got all this information there, and it's all crowded onto a small laptop. That doesn't make life that easy. So we go across to here. If we want to look at something and give yourself some more room to do it, you just press F6, and that particular component that you're highlighted on will become full screen. And look, we just landed on all the help for this new parameter for boost control, which we'll talk about in another webinar. So clicking on here explains all about this throttle position minimum parameter. It even gives you a little diagram. Alright, so pressing F6 simply highlights or simply goes to full screen for anywhere you happen to have highlighted. So if I highlight on here, see how this has gone orange? F6, F6. Alright, so it's a really good way of, if there's a particular screen that's detailed. With this GP Lite package, we've tried to spread things out a bit better through the worksheets, and also remove unnecessary channels and items from the worksheets, so as we can simplify things. So I haven't really got an overly crowded worksheet to show you. Ref sync, that's an example. Alright, so that's pretty busy. So maybe you want to see something like that. It's still not too bad. Alright, so that's that. Channels on and off, and some not many in GP Lite, but in some of our other packages the list of setup tables and parameters and channels can be quite long, and sometimes if you're offline then you don't want to see the channels. So this little squiggly line here that appears on the search bar, then you can click that, or Shift C I believe it is as a shortcut. I'll just check that in a minute. Gets rid of these channels. So these are live channels that on a long list of setup parameters and things, they can make life a little busy. So that's a way of clicking that on and off. Let me have a look for you. Okay, so if I go to all calibrate, I can switch to list view. Right, you can see all these channels here. They're not a table or a parameter or anything like that. These are just channels. So I can click them on and off here. Alright, see they're gone, and now with them gone I just have either tables or parameters to view. Alright, and Shift C. Yeah, Shift C is the shortcut for that. Okay. Alright, and the other one is if you've got a file from someone else and there's a lot of sensors that have been configured on there that you don't need. The M1 has an auto hiding process where if you unconfigure the sensor, then all the setup disappears. So if you don't need that sensor, then unconfigure it. If it's got, say, an exhaust temperature sensor configured in the setup, then one, it'll be an error, so the ECU will be flashing the error at you. And the other thing is all the exhaust temperature setup parameters will be there waiting on you to configure them. But of course, if you haven't got an exhaust temp sensor, then you don't need it. So unconfigure the sensor, and then that will get rid of some more channels out of the road. Okay, now you've probably already worked this out. Live data changes happen instantly, so just like all our ECUs, once you start entering information, if you're online, that change is instantaneous. But one thing that is very different from the Gold Box series is that it doesn't automatically save them. So with the M1, if you want to permanently save the changes you've made into the ECU, you need to save them. So there's an icon for saving, or the easiest way is just Control S. So get used to pressing Control S, and that will permanently save your changes into the ECU itself. Let me just show you live. Okay. Alright, so here we are. Let's go to the efficiency table here. I can press the space bar and go to the live site. So I might want to make these changes. Might want to just highlight this area here. Let me put some engine speed on and maybe get to a bit better sight. Or if I press spacebar, we're now right on the 60 kPa and 1500 engine speed sight, and I might decide I want to put a number of 80 there. And the moment I do that, you'll notice that this top bar up here went yellow. So what that means is it's saying, hey, you've made a change. The ECU is using that change, but it's not saved in the ECU. So to save it, we can either click on the Windows Save icon, or if I push down Control S. Now the very first time I do this, because it's the first save I've made since I've opened Tune, it's going to do that. And the other thing that I didn't point out was there's a little diamond there that said that that side had been changed. So if we change it again, maybe I'll drop it to 78. So you see again, we've got save required coming down the bottom here. This going to orange and the diamond there. So I press Control S and it all goes away. Alright, now if you happen to go offline and you've forgotten to save, the laptop of course still has your tune up there. The laptop doesn't lose it, but the ECU, if you go offline, will revert back to the last save. So if that happens, you forget to save, all you've got to do if you do go offline, so if I let's say I've just turned the ECU off here, the engine's off, you'll see we're not connected. Whoops, I haven't done that scenario properly for you. I need to make a change first. Just wait for it to reconnect. So here we are on this one here, use the quick launch. Alright, so back to my scenario, make a change. Alright, so we have a diamond there, and now say I turn the engine off, or the Ethernet cable falls out, or something like that, unexpected. Okay, the ECU's gone offline. Alright, we can still see that we've got something that hasn't been sent to the ECU. It's looking for the Ethernet cable, looking for the connection to go to the ECU. So maybe the engine stalled, ran out of fuel, I don't know. So now all we do is File, Save As. We can save that as a new file. I can push P1. Okay, and then next time I go online, reconnect, fix the Ethernet cable, whatever. So I can see I I can see my ECU is, if I look here, I can see there's my ECU. There's multiple ECUs online here. That's because I'm at MoTeC head office and we're on the Ethernet on network, so all these other ECUs are online as well, but this is the one I want. So I know that's there. This package is addressed to 4357, so if I just press send, it'll send that saved data back to the ECU and go on to line. Alright, so key point here is you keep pressing Control S or saving your work as you go, and if you don't end up doing that for whatever reason, it's not a disaster. You just have to save it as a new file and then send it back. Okay. Alright, so we've covered most of that. The other thing to note there is about these little red flags. What do they mean? If you change a parameter, and this is normally just related to parameters, you change a parameter and it's got one of these red flags, what that means is that's a significant change inside the ECU firmware, and it will need to reset in order to utilize that new parameter. So when you press enter and Control S on this, it's going to do a full reset, at which point you'll get a warning. And so if you're at full throttle running down the road, then that's probably not a great idea. So you need to reduce power, come back to idle and press Control S, and then depending on the engine and so forth, sometimes it'll stall, but it certainly goes through a full reset. So, and you'll see the instead of the bar going orange for a save, it actually goes red this time to warn you that a reset is required to use that particular parameter. The other thing that turns up next to those little flags is the Q function. Now in gold box days, Q was only used for quick Lambda. In the M1 series of ECUs, we use Q quite often to quick calibrate, stands for. So in the case of setting the throttle position, highs and lows, in an M1 it's called offset and scale. We in this case it's a pedal setting, and we have the pedal right off, and we press Q and it enters that number direct into the software. Alright, so Q means quick calibrate. It's also used in the M1 for quick Lambda, but also used for other parameters through the software. Alright, if you've seen some webinars before now, you'll know about this, our live data control and pressing T. It's one of the really nice features about M1s. So we can pause our data, unlike in the M800s and so forth, where that data just disappears on the chart recorder. So in our time distance graphs or chart recorders, we can pause data like that, and it's just like having instant data logging. So when we do that, I'll show you shortly live, the connected bar flashes to show you that you are paused, and then effectively it's almost exactly the same as using data in our I2 analysis software. So we can go back in time, sometimes up to 20 minutes or so, and go and have a look at information, what the Lambda was, did we have an error, did it overboost. So you're instantly looking at log data, and you can then make changes based on that. So really nice feature. It absolutely massively speeds up tuning. You can quick Lambda backwards after the fact using that, and we'll show you some of that stuff coming up, but I'll just show you how that works. Right, so here it is. We're online with a simulator. Let me wobble the engine speed up and down here, and the manifold pressure. Okay, you can see things moving around. So we can actually do this. Maybe you drive around the block, you take the car for a full throttle pass down a racetrack or something, although you wouldn't normally have a laptop in for that. But you do some logging. As I say, a ramp run on the dyno is pretty typical, and at the end of that ramp run you want to see what happens. So we just, if you look up here, everything's normal for connected. If we push T, everything stops here, And at this point is a time that I use F6 a lot. I click into this area here. See how it's got orange around the outside here? If I press F6, this now is exactly like log data in our analysis software. So I can just roll out with my mouse or go to F2. I can double click, drag, click, and look at any particular information here. And in fact, the whole software right across the range is all zoom linked to this. So what that means is if I press F6 again, anywhere in the software I go, it's all paused at that same point. So I can look at what was happening with my ignition, I can look at what was happening with my boost control, I can go through all of the software and have a look at the data, make changes. Once I'm done, I just press T and off I go, and it carries on back to normal. Really, really useful feature. Okay, here we're talking about the Q key again, and almost exclusively you're going to use just the Q, the quick Lambda here. So for anyone who's tuned any of our ECUs in the past, you'll recognize and have used this key, I'm sure. So what that does is, normally on a gold box it just did quick Lambda, and so I'll just show you it working here doing that. And that's the most common use of it. So L is used similar to the way it was, which is Lambda was. So if you're offline and you've got no paused data at all, you can still look at some log data. Say someone sent you some log data, and you can go back and use the L function in the same fashion you did on the gold boxes. So let me just give you a demo of that now. Alright, so we can actually still, that data that I showed you before will still be in the cache of the laptop. So let me just pause it by pressing T, and we can go back. Here it is. I just scroll back with the mouse, and we can go to a point here. Let's go to our efficiency map. Alright, so at this particular point I can zoom in and say, right, at 2805 I have a Lambda error and I want to fix it. Now you may choose to, because normally you would put this on site, so in other words you would normally put the engine at 3000 or 2500 and tune a site, but we could actually, if we wanted here, put in a 2800 site. So it's useful for me to show you how to do that. Click up here, press A for axes, and we're going in to add a 2800 site. So 2800, enter, OK, here's our 2800 site. Okay, and we can see here the highlighted part of where the engine was at this time, and without even being here, this is after the fact, the engine's now idling, let's say, or even turned off. You can pause this data, take out the Ethernet cable, go back to your office and do this all offline. And so I can, if I put this on the site I want to tune and I press Q, it will look up what the fuel mixture aim was for that exact time. This is all the details here. Let's bring my mouse back, of what the engine, what state the engine was. Alright, what the Lambda was at the time, where the closed loop fuel is at the time, because if this actually works even with closed loop on, but let's just forget that for now. So if there is an error in the between the Lambda aim and the actual Lambda, it's displayed here, and we just press apply. So if we look at it now, our fuel mixture aim is 0.88, our Lambda is leaner than that, then the number should go up. So if I press apply here, it's lifted the number. It's you'll see all the diamonds from where we've added the extra row, so that's all new information, and that's why it's all marked. And because we've done a quick Lambda point, it's also put a black square there, it's highlighted it, so whenever you tune on site like this, it highlights that as a known good site. Now on that subject, if you want to click over here and you can force your own site, you might decide, oh, I'm going to make that change, make that number there 80, and because you weren't on site and live at that time, it didn't put the the black box there as a marked site, but you can just press backspace and it puts it there as a known good site. So later, when you come to smooth things out a little bit, anywhere where there's a black mark like that, you know that's been a site as a trusted site, a site that you don't really want to change, and so you may end up smoothing numbers around those known good sites. Okay, enough of that. Alright, so that's some tuning methods. Before you turn the key and get into this thing, it's good to do some testing. So if you've got this thing wired and set up right, then this test should go without a hitch. But you can test all your coils, your injectors, your outputs, your sensors, and make sure everything is correct. So before you even turn the key for that first time, we want to have a look and make sure, for example, our air temp and our engine temp read the same. If the engine's never been going or hasn't been started for the day, then they both should be the same. Make sure the throttle works. Everything is looking sensible here. Go through the test procedure for the coils and the injectors, which we cover in a separate webinar, and make sure all the sensors are working well. Alright, and then if there are any diagnostics which flash down the bottom, I'll just show you what that looks like. Here it is. See, we've got some diagnostics down here, and that'll be because we're on the simulator. So if I hover over that with my mouse, it tells me what the shortcut is. So if I press F3, it's appeared on my other screen, drag it over here. So this will give you a list of things that aren't right. So I can see my Lambda control's not working at the moment, and that's because I'm on my simulator, so I haven't got a real Lambda LTC here, and my fuel pressure sensor's in low fault. So you might want to have a look and see what's going on there and fix that. Now you'll see here that but hey, hang on, this has got fuel pressure. But what this fuel pressure is because the fuel pressure sensor is in error, it's looking at the fuel pressure default and modeling what it thinks fuel pressure should be. It's better than using 0. Alright, so just because you have a fuel pressure channel, it doesn't mean that your fuel pressure sensor is working. Alright, so long story short, make sure you've got all your errors sorted out. No point in tuning if you've got a problem with a sensor or a sensor's badly calibrated, coils aren't wired right. Get all that sorted out before you even turn the key, and then when you do go to turn the key, it's going to give you a really good result. 2.6. Alright, sorry, a little bit out of sequence. Before you do turn that key, we need to make sure that we have some sensible numbers in tables. So we'll quickly go through that. The understanding is that you guys do have some tuning experience, so when it comes to being presented with an ignition timing table, you have some idea of what to do. With regard to GP Lite, one of the few things that don't migrate from the GP Lite or that don't migrate into the GP Lite package from other GP packages is the ignition map. And so this is the way to do that if you have a GPA ignition map or a GPR ignition map that you want to use as your starting point. So there is a separate webinar telling you how to do this, but the short version is go into your GPR or A. Well, first of all, add your GPA ignition map file as a compare. Go in and export that ignition map to clipboard. So right click, export to clipboard, go over to the GP Lite ignition map, right click and import from clipboard, and it's as simple as that, and the ignition map comes in. Alright, other than that, without getting into the detail too much of what to expect for ignition, smaller numbers at idle, higher numbers at higher engine speeds, and then lower numbers again as load comes on. Every engine's different, that's why ignition maps are something quite common to be migrated over, because they are very different depending on the fuel, depending on the engine, depending on the boost. But perhaps once we get tuning, we can talk about that some more. Alright, fuel mixture aim, again, you should have some idea of the lambda that you want to run prior to your tuning. And unlike a gold box, the M1 is always using this lambda aim table, fuel mixture aim table. So it's part of its calculation. So if you change any of these numbers in here, the fueling or the end result will change. So the idea is you specify exactly what you want in here. When you tune, if it's not meeting the aim, you change the efficiency table to suit. Okay, so in the M1 we have a few of these mixture aim tables. So we have the fuel mixture aim main, and you put in your normal or your target lambdas in here. And as you can see in this table, somewhere near lambda 1 for a late model engine for idle and cruising, often between 0.99 and 0.9 for the lower pressure areas. So manifold pressures under 60. Then basically the more load on the engine, then the richer you will need to go, and the higher the engine speed, sometimes the richer you'll need to go. There's lots of reasons for all that, which we're not going to talk about now. But this is your target lambda. Now there are some overrides for this target lambda. This fuel mixture aim table has overrides, and so they're listed on the next page. So as an example, we have an inlet air temperature override, or a table that if the number in this table is ever richer than the number in the main, then the ECU uses the number from the richer table. So in other words, the ECU scans all the fuel mixture aim tables and chooses the richest aim and uses that. Okay, so all of those tables appear in the tuning fuel mixture aim worksheet. So we need to fill those out. Alright, so this page is just covering off what we've said. There's an A and a B, fuel mixture aim, engine temp, exhaust temp, just a number of tables that appear on that fuel mixture aim worksheet. And again, richest of the tables is used. And the fuel mixture aim state, so there is a channel called fuel mixture aim state, and that will actually tell you which of all of those tables is the one that's currently winning the war, if you like, the one that's being used by the M1 to control the fuel mixture aim, or control the lambda 2. So if you want any of these tables to have no use at all, then you put a really high lambda number in them. So lambda 2 or 10 or whatever, and as long as the number is higher than your richest number in the fuel mixture aim main. Right, the A and the B fuel mixture aim tables, that refers to a switch that you can set up for running two different lambda aims, fuel mixture aims. Okay, there's just basically a flowchart of what happens. All the aim tables, richest one chosen, and this one becomes the fuel mixture aim channel. Alright, so this is a little diagram of just demonstrating how well this system works. So I captured this data quite some time ago. The purple squiggly line there, that's the real lambda channel, and depending on, and I went in on this capture and just made different fuel mixture aim tables richer, and as I'm doing that, you can see the fuel mixture aim state is changing through the different tables. Alright, so what I really want to demonstrate here though is, so different tables can affect the lambda when it's the richest number, but the other thing is, if you set this the ECU up properly, the lambda will just follow the aim. Now this is without closed loop. So the moment the aim channel goes to a new value, then you'll see the lambda just goes there. Alright, so the ECU sees the aim change request, automatically calculates the pulse width that is required to meet that aim, and delivers it. So this is actually even faster than closed loop, because closed loop goes based on the error, so it has to see an error in order to correct it. So if you do the setup properly and your injector calibrations and things like that, you can expect something pretty good like this. So in order, once you've tuned the engine, if you want to make the engine richer or leaner for any reason, maybe you want to start richer for safety, and as time goes on you want to lean the engine up, you don't change the engine efficiency numbers to make the engine leaner, you change the aim. Alright, so just stressing that again back in this in the software. After the engine is tuned in the efficiency map, then if we want to later down the path for any reason to make the engine richer or leaner, so we want to take 10% out of this area, it's a little rich for whatever reason, we can simply in here we can page down, we can type in a new number, or I can go to my keyboard and go times which one am I going, leaner or richer? I'm going leaner times 1.1. Alright, so that's now 10% leaner than before. But I don't like that, so I went the wrong way. If I go Control Z, I revert back. Okay, so once the engine is tuned well, then fuel aim changes, or richer or leaner aim changes, you should come in here. This is what the closed loop follows. This is what the open loop or the normal calculation follows. Not here, not in the efficiency map. Okay, this is just this table is actually just to tell the ECU how much air is flowing through the engine. This table tells the ECU how rich you want the engine to be. Got it? Alright, just quickly, fuel timing, very similar to the gold box. I mean, it's just the same. You have inlet manifold pressure and engine speed. You have a fuel timing table. In the GP Lite package, it's hard coded to the trailing edge or end of injection. The only thing of note is that you can't ask for fuel timing to end after 120 degrees. If you do, well, realistically, any fuel going in after 120 degrees is definitely going into the wrong cycle. It's not going into that cycle because the inlet valve will be closed. So for that reason, the pulse will actually be shortened anything after 120 degrees. So we don't expect you to be tuning in that area, but just be aware that if you try going less than 120 degrees in your fuel timing, that's the result. Alright, so here's our injection pulse. If for some reason you want to run more retarded fuel timing than 120 degrees, the pulse is shortened, so it'll actually effectively lean the engine out. Alright, so that's it for setup. I know that went on a little long, sorry about that, but hopefully we covered some good information for you, and thanks for listening, and we'll catch you on the next one.